Now let us move on to the next class of elementary signals. That's really important. Again, we are this is going to be a review for you. We are going to look at continuous time, sinusoid and discrete time. So let us look at, rather than sinusoidal, it's more correct to call them as exponential signals. So what you are used to in terms of continuous time exponential is a times e to the s naught t. A is really a complex number, magnitude a times e to the j phi, and s naught is really another complex number which is a sigma naught plus j cap omega naught. Therefore, x of t, which is a times e to the s naught t, is really magnitude a, and e to the s naught t can be written as e to the sigma naught t plus j cap omega naught t. So therefore, this becomes e to the sigma naught t, e to the j omega naught t plus phi, right? And the real part, of course, is cos omega naught t, and the imaginary part is right. So these are the real and imaginary parts, and the picture associated with this is something like this. And remember, this is what is called as the everlasting exponential, and so a rough picture. So these are the real and imaginary parts. Now the counterpart is x naught of n, x of n, which is a times z naught to the n, and a is the same as before, magnitude times e to the j phi. Z naught is again a complex number, and z naught is r naught e to the j omega naught. By the way, so s naught, which is the complex number, we wrote it as sigma naught plus j cap omega naught. This is in Cartesian form, whereas the complex number z naught, we are writing it as r naught e to the j omega naught, which is in polar form. So this is and this, of course, is polar. Why is that? So you have seen this before, right? You have seen both continuous and discrete time were introduced in signals and systems, right? And signals and systems, typically it was introduced like in this form, the way I am introducing it now, correct? So did it occur to you as to why one representation is used for continuous time and the other representation is used for discrete time? Very simple. Yes? I'm sorry, I didn't hear you. I'm not sure I follow your answer. Okay, but you were introduced to the discrete time exponential, were you or were you not? If you are not introduced, then probably it's not a fair question. So you were not, I know the signals and systems, mainly it's continuous time, but some amount of discrete time, was it part of the syllabus or no? Okay. All right. Okay, but were you introduced to this? Okay, even if you introduced very briefly, the very fact that you were introduced to it should raise this question, right? Hey, why is that in Cartesian whereas this is in polar? Natural frequency. Why is that not natural there? So, have you had a course in complex variables? No, okay, that's a very good excuse. No, but even then you might be familiar with this. If you are going to raise a complex number to the nth power, what do you use? No, what's the theorem, mathematical theorem that's used to? Okay. Let not the French hear us pronounce that, but that's the theorem that we use. Here you are going to raise this complex number to the nth power, and if you are going to raise a complex number to the nth power, the easiest thing would be to express that in polar form and then proceed. All right. So, this becomes magnitude times magnitude of A times R naught power n e to the j omega naught n plus phi, and of course similar and the imaginary part is plus phi. And the reason why you are using polar form is de Moivre's theorem, and raising a complex number to the nth power where n is an integer, that theorem makes this very simple. That is the reason why you are using polar form here and Cartesian form for the continuous time case. And then in terms of pictures, again you can plot two different plots here. In my cleaned up notes I will put up MATLAB generated plots, which is very accurate. Here I am just going to give you some feel. So, this is the so called stem plot, right. The independent axis will be n, and then you will plot the samples of x of n, real part versus n, imaginary part versus n. So, looks like these two are very, very similar. One after all seems to be the taking sample values of the other. Now, let us probe the similarities and differences a little more. To get a better understanding of this, so let us focus on e to the j omega naught t. Here we are trying to compare and contrast continuous time sinusoids versus discrete time sinusoids. So, here just to make sure everything is in place, this is an everlasting exponential. So, this goes from minus infinity to plus infinity, and if sigma naught were negative, for positive values of time the envelope will decay, whereas it will blow up for negative values of t. On the other hand, if sigma naught were positive, for positive values of t the envelope will be exponentially growing, whereas for negative values of t it will be decaying, and if sigma naught were 0 the envelope will be constant. That is when you will have your sinusoid, and if cap omega naught were 0, then this will be purely a real valued exponential, right. Of course, assuming we are having the amplitude also to be real valued. And the corresponding counterpart here, the role of sigma naught is now played by R naught. So, if R naught were less than 1, then for all positive values of n, the envelope will decay, whereas for negative values of n, the envelope will blow up. If R naught were greater than 1, positive values of n, the envelope will blow up, for negative values of n, the envelope will decay. And similarly, if little omega naught were 0, you will get the corresponding counterpart for the case where cap omega naught was 0. Again, if you assume the n amplitude A to be real valued, you will get a pure exponential. We will again delve into a little more of this as we go along. So, looks like these two are very, very similar. Now, are there differences? To see what the differences are, we focus on e power j cap omega naught t. So, this is a pure complex exponential. And x of t plus cap t equals x of little t. That is, this signal e power j cap omega naught t is periodic with period cap t, implies that t is what is the value of t for this signal? 2 pi by omega naught. Is this correct? No, remember cap t is the smallest number for which this is true, right. So, this is not fully correct, there is something not quite right with this formula for cap t. Okay, yeah, that's, yeah, omega naught not being 0 is fine. Suppose omega naught is not being 0, is this still correct? Yeah. No, remember cap t is the smallest number for which this has to be true, right? Okay, non-zero number. So, what change do you have to make? Okay, no, just following up on what was said. Smallest non-zero, can you follow up on that and then correct the error in this formula? No, where will n come? N won't come here. Ah, okay. What is missing is this, right? Because we need the smallest non-negative number. So, this is always periodic with period cap t, no matter what omega naught is, this is always periodic with. So, the first important implication is this is always periodic, and the other important thing is as omega naught increases, the what can you say about the rapidity of the oscillations? It will also increase. The rapidity of the oscillations increases, and there is no upper bound on omega naught, right? Mod omega naught, there is no upper bound, right? So, omega naught belongs to the interval 0 to infinity. So, very natural to ask this question about the discrete time counterpart e to the j little omega naught n. Say that again. Because omega naught can also be the DC signal, correct? there is no problem with omega naught being 0, that will give you the DC signal, right. For the DC signal, what is the period, that is a minor issue, but omega naught can indeed take on the value 0, which will give you your familiar DC signal. Now let us ask the same question for its discrete time counterpart. We will ask these two questions: is x of n always periodic? As omega naught increases, the signal oscillate more and more rapidly. So these are the counterparts of the question that are clear for the continuous time case. Suppose we consider two different frequencies, omega naught and omega naught plus 2 pi, right. Then x of e to the j omega 1 n, which is e to the j omega naught plus 2 pi times n. So this is exactly x of n, because this is nothing but e to the j omega naught n times e to the j 2 pi n. E to the j 2 pi n of course is 1. So note that omega 1 is strictly greater than omega naught. So you get exact same signal if you replace. Let us look at an actual signal, let us vary omega naught. So this suggests that as far as the signal is concerned, omega naught can be replaced by omega naught mod 2 pi. So this is a symbol we are going to use in this context. So this is nothing but omega naught mod 2 pi. Now what we are going to do is, we are going to keep on increasing omega naught, and we see that omega naught and omega naught plus 2 pi will yield the identical signal. Therefore, if omega naught is 0, this implies that x of n is 1. In our language this is called as the DC sequence. You will also get exactly the DC sequence when omega naught is 2 pi, because omega naught and omega naught plus 2 pi are the same. Therefore, you get an identical signal when you increase the frequency from 0 and make it 2 pi. Again the DC sequence comes. So this leaves us with the question, what happens to the rapidity of the oscillations as omega naught increases from 0 to 2 pi. So what we will do is, we will look at a simple real valued sinusoid. We will vary the frequency of oscillation from 0 to 2 pi, and then we will see how the oscillations vary. Do they increase? If they do increase, then it appears that you will have to have a maximum rapidity of oscillations, and then the reason why this has to be true is because again when you keep on further increasing omega naught, when you hit 2 pi you will have to get back the same DC sequence. So intuitively it appears the frequency of oscillation will increase and then probably start to decrease and then slow down and reach the DC sequence once more. So we will look at waveforms next class.